Right, okay, in this video we're going to talk about nucleosynthesis. And this is the process by which we make elements. So we're going to look at it from two perspectives. One really briefly on the main sequence, and then we're going to look at red giants and red supergiants as well. And look at how heavier elements are made inside stars. So generally the main sequence, just quickly, just to give you an idea, so the main sequence forms through the proton-proton cycle, where we have a proton and a proton coming together to make deuterium. So deuterium is like a heavy hydrogen, it's got an extra neutron. Obviously you can imagine we're giving off some positivity here. So we've got a form of beta decay occurring at this stage here. And then what we do is we add another proton to this situation here, and we make helium. So this is helium-3 now, so He3, so it's two protons and a neutron. And then we combine another helium-3 that's been made in this same process together with this one, and we give our standard helium-4, so helium-4. So that's the standard helium element there, and as a result of that interaction we actually give off two protons as well. So the net kind of change of protons in a star is 4 protons or 4 hydrogens is used per one of these cycles, and this is the standard cycle for a star. However, so that's main sequence, and we're not going to talk too much more about that other than just to say that's what happens in a main sequence star. What we are going to talk about, however, is we're going to talk about what happens in a red giant and a red supergiant, and so giants and supergiants. Now, inside stars, the whole point in a star is to fuse heavier and heavier elements. So obviously all the fusion happens in the core. And in the core we start out with hydrogen, and it leads to helium. And eventually, because the star is hotter, it becomes a red, much larger, it becomes a red giant. So at this point, red giant, from brackets there, at this point we can now fuse much heavier elements like carbon and oxygen. And the cool thing about that is that we can keep going and keep going and keep going, and you hopefully will remember from studying binding energy, or if not, you want to go back and have a look at the video, that we can fuse elements all the way up to, generally, for the most massive stars, up to iron. This is iron 56, so that's the atomic mass number of iron. So how do we even get heavier elements? Because if all our elements are fused inside stars, well, how do we get heavier than iron? Because as you will hopefully remember, and if you don't, you will want to go back and have a look at this, the binding energy curve suggests that we only get energy up to fusing from iron, up to iron. Anything else, we're going to lose energy. We're going to be a net intake of energy. So this is the binding energy per nucleon graph, and this is the number of nucleons here. So again, I'm not going to go over that in too much detail. Go back, have a look. I've got a whole video about this graph very specifically. But iron is the value that where energy can be got from the. We can't get any more energy from it when it starts trying to fuse up to iron. It can't fuse iron with anything else to get energy from it. So when we made iron, that's basically the end of the road for this star. But as we well know, there are heavier elements in the universe than iron. So what kind of elements, how are these elements made in stars? Well, there's 2 ways we can make them. One is by the S process, and one is by the R process. I'm going to talk about these 2 processes now, just briefly, just to give you an idea of the kinds of ways in which we can make elements that are bigger than iron, but not necessarily through the standard fusion route in order to make them. So we'll start out with the S process. So the S process is termed that because it's the slow process. S for slow. Well, what's slow about it is the fact that it happens just over time, very gradually, through the general interactions of elements inside the star, inside the red giant. So when it becomes a red giant, it's very hot, very dense, and so it's got a lot of gravity pulling all those elements together, and it's going to be able to shove them together. Now, this slow process is to do with neutron capture. Now, the cool thing about neutrons is that they are neutral. They have no charge. And that zero charge allows them to do something very, very specific indeed. It allows them to attach to elements without the problem of electrostatic repulsion. Because if we go up here and if we think about standard kind of this relationship here, well, this relationship here is two protons or two hydrogens that are having to come together against that electrostatic repulsion. And so once electrostatic repulsion is overcome, then they get close enough, then the strong nuclear can take over. And they join together and we get this process right here. So what happens with neutrons and neutron capture? Well, if you have an element, for example, so there's our element, and let's say it's got 4 protons in it. And we've got a neutron with very high energy because obviously we've done this fusion process. There's plenty of energy in this star. So this neutron is going to have lots and lots of energy. Bear in mind, you might ask yourself, where do these neutrons come from? Some of these fusion reactions actually give off neutrons as a result of them happening as well. So if you're in a kind of a quandary about where are these rogue neutrons coming from, they can occur as a result of fusion reactions. So we've got our neutron over here, and obviously it doesn't suffer with the same problem of the electrostatic repulsion over here. It's not repelled by the electrostatic positive charge of the nucleus. And so as a result, we can join this neutron to this nucleus, because once it gets close enough, as happens here, the strong nuclear takes over. So strong nuclear force takes over, and so we have now got an element. You should count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've now got an element with an extra neutron in it. Okay? Let's identify that extra neutron here. So there's that extra neutron that we've just added in there through neutron capture. Well, this can keep happening and we could get more neutrons added slowly but surely, and we might get an element that's much, much bigger. But what will happen eventually? You should hopefully remember that what happens when we have too many neutrons? Well, too many neutrons causes a very specific type of decay. What happens is we get beta decay, and that's beta negative decay. So this neutron is going to become a proton by giving off some negativity in form of an electron. So we can write this whole process out to be a neutron goes to a proton plus our beta minus particle plus obviously our anti-electron neutrino. And this is also a source of neutrinos in stars. So when people say there are a lot of neutrinos in stars, these reactions, and obviously the positron given off here is another source of neutrinos as well. Actually, that's just a normal electron neutrino in that case. So, so in this form of reaction, we're getting these anti-electron neutrinos to balance the lepton number. Again, go back, have a look at that idea in some of the previous videos if you're not sure what I mean by lepton number. So we've got this situation here. So neutron capture leads to excess number of neutrons. The excess number of neutrons can cause beta decay, which leads to, we've effectively created an element now with 5 protons. And it's bigger. It's much, much bigger. Hopefully you can see that on the video there. Okay, so we've made a much bigger element, and so as a result of that, we can say, right, okay, we've got a bigger element, and we could keep adding neutrons, and believe it or not, we can then make things all the way up to bismuth, which bismuth can have a mass number of 209, and that is a big old element, much, much bigger than, say, iron 56. Iron 56 is the biggest we can get via fusion and get energy out, but through this process of neutron capture and beta decay, we can get much bigger elements indeed. So just to sum up that process, neutron capture leads to beta decay, which leads to heavier elements. Okay, so in that circumstance, we can create heavier elements. But obviously, we've talked about the S process now. Now we should talk about the R process. I'm going to use a new page to do that, though. So the R process. Well, what is the R process? Well, the R process is the opposite of slow. It's, hopefully you guessed it, rapid. So a rapid process will happen when we have lots and lots of energy, very high density, and we are going to have plenty and plenty of neutrons flying around with that high energy. Yep, you guessed it, it's a supernova. So a supernova occurs, and as a result of that supernova, we have lots and lots of energy and lots of free neutrons, which is really, really going to be likely at this stage because they've got so much energy as a result of this supernova. So we get rapid neutron capture. And obviously, when that rapid neutron capture happens, we can make much, much heavier elements all the way up to, like uranium, plutonium, all those lanthanide, actinide series that can allow for, that radioactive decay via alpha even at this stage, because that neutron capture happens so quickly. And then obviously we'll still get that beta decay to allow them to be those heavier elements with more protons. But the idea is that this rapid effect of the supernova causes much heavier elements to form. It's effectively the same process. You've got your element here, but instead of just this slow one neutron at a time, instead you've got lots and lots of neutrons all smacking into nuclei all at the same time, and they're all jumping in there, and we're getting the beta decay as well, and it's all happening so quickly, and we get these absolutely massive nuclei. And I'm not going to draw lots and lots of circles, you just get the idea. I'm going to draw a few just to give you the kind of theatrical thought process where we get lots and lots of huge elements created as a result of this rapid process that occurs when a supernova occurs. It's the same process for the most part as in the slow one, except the idea is that it can only form up to, say, things like bismuth, but in this circumstance here we can form much, much heavier elements indeed. So what happens is we're going to look at the different types of supernova in the next video, and we're going to talk about how we can use those as standard candles.